Hey everyone, this is Dr. Walker. In this video, we're going to go over an example with electric dipoles, finding the dipole moment and the torque on a dipole. We are given in this problem that we have a dipole that carries 2 nanocoulomb charges, so that is the charge Q. And we are given the coordinates of the positive and negative charge. We can draw them just to help us visualize since it's our first time. I'm going to have the negative charge over here somewhere and a positive charge over here somewhere. And we know that the dipole moment is directed from the negative charge to the positive charge. So how do we find the electric dipole moment of the object? We can use a definition that we multiply the charge times that position vector that we can call d or 2a. In this case, I'll just call it d. So the charge is 2 times 10 to the negative 9, that's in coulombs, and then we need that position vector. So we know that we have to go in the x direction to the left and then the y direction upward. The distance that we're going to go into x direction is going to be the negative 1.2 minus the 1.3 here. That's going to be in millimeters, so times 10 to the negative 3. That's going to be in the I direction. And then in the j direction, it's going to be the 1.4 minus the negative 130, right? The 2.7 millimeters that we're going to go up. So 1.4 minus negative 1.3 times 10 to the negative 3 in the y direction. So we can go ahead and simplify a little bit. 2 times 10 to the negative 9. And we're going to get a negative 2.5 times 10 to the negative 3 plus a 2.7 times 10 to the negative 3. Finally, we need to multiply it by the charge, and that's going to give us negative 5 times 10 to the negative 12 in the I direction plus 5.4 times 10 to the negative 12 in the j direction. That's going to be our dipole moment. Let's not forget our units is a charge times a distance, so it's a coulomb times meters. Let's take a look at the second part. This time we're trying to find a torque acting on the dipole if it is placed in an electric field that has this direction. So let's write down our result from the previous slide. I forgot to write it down earlier. So dipole moment is negative 5 times 10 to negative 12 in the I direction plus 5.4 times 10 to the negative 12 in the j direction. That was our dipole moment. And now we need to find a torque, which we know is equal to the cross product P cross E. If you remember how to do a cross product, if you are given vectors in unit vector notation, then the easiest way is to write down the determinant. So you can write it in 3D if it helps you. It was always easier for me in 3D. So we're going to do the P first, right, and then the E here. So P is going to be the negative 5 times 10 to the negative 12. The J is 5.4 times 10 to the negative 12. The K is 0. And then the E, the I component, is 7.8 times 10 to the third, negative 4.9 times 10 to the third, and 0 in the Z direction. So to find the determinant, we know that in the I direction, we're going to have nothing because we're finding the determinant here, and we have zeros that we're multiplying 5 times 5.4 times 0 minus 4.9 times 0. So we have nothing in the x direction. We have nothing in the j direction because we have 0 in the k again. But in the k direction, that's where we're going to look at the determinant right here. So we're going to have -5 times 10 to the -12 multiplied by -4.9 times 10 to the third. So we have this times this minus this times this. So minus 5.4 times 10 to the -12 times 7.8 times 10 to the third. So that's how we do our determinant. And all of that will be in the k direction. It's going to give us -1.76 times 10 to the -8 in the k direction. And let's not forget our units again. Torque, you can see newtons divided by coulombs times meters is going to give us newtons times meters. So I did want to add one quick thing since we have another minute. I didn't write a part to find the energy of a dipole, but you should be able to find the energy of a dipole. You should be able to do the dot product, -p dot E. So just as a reminder, we're not going to do it here, but just as a reminder, you just multiply the x components, and then you multiply the y components. If there was a z component, you'd add those, and you add it all together to get the dot product. So you should definitely review that in case you do need to calculate the potential energy of the dipole in the electric field.